Hi friends, let's learn Newton's laws of motion in a more exciting and practical way. With the help of some simple examples, I want to show that these laws of motion are not just limited to your physics textbook, but they are happening all around us in our everyday lives. And after we do the 3 laws of motion, we'll finish off with our top 3 questions on this topic. I'm sure by the end of this video, the concepts are going to be super clear to you. Now, before we start, let's do a quick recap of the 3 laws of motion. Here are the statements of the first law, second law, and third law of motion. Now I'm going to show you some simple everyday examples, and you try to decide which law is applicable. Is it Newton's first law, second law, or third law of motion? These type of questions are quite popular in the test, where they give you an example and ask you to explain based on one of these laws. So get ready to put on your thinking glasses. Are you ready? Let's start. I'm sure you've heard it's important to fasten your seat belt when you're in a car. Now let's see which law it's based on. Are you ready? Let's go for a drive. Now if the person driving suddenly has to apply the brakes, did you see what happened? I was thrown forward. If I wasn't wearing my seat belt, I would have hit the front seat in front of me. Or if I was driving, I would have hit the windscreen. So which law of motion applies to this situation? What do you think? The correct answer is Newton's first law of motion. This law deals with the inertia of rest and inertia of motion. Now let's see which type of inertia applies here. When the car is moving, since I'm sitting in the car, I'm also in motion. Now when the brakes are applied, the car comes to a stop. But I'm in motion due to my inertia of motion. So I get thrown forward due to the inertia of motion. So it's Newton's first law of motion that talks about inertia, which applies to this situation. Now I've reached home. So what's the moral of the story? Always be safe and fasten your seat belts. I'm going to get off now and go for a walk. Now let's look at a simple example such as walking. So while you're walking, which law of motion applies here? That's right, it's Newton's third law. Now let's take a closer look. When you're walking, your feet are pushing the ground. Your feet are applying a backward force on the ground. The ground in turn applies a forward force on our feet, pushing us forward and making us move. Can you see the action-reaction pair? Action is our force on the ground, and reaction is the force of the ground on us. The two are equal and opposite. So it's Newton's third law of motion. Every action has an equal and opposite reaction. And this law explains how we walk. Let's say you're playing a game like cricket or baseball. Here I have a cricket ball with me. The coaches teach you to take the catch like this, with your hands moving down. But if you take the catch like this, ouch! Since the ball is pretty heavy, it can hurt your fingers or it can bounce off your hand. But if you take the catch like this, it doesn't hurt your hand. Why is that? Which law will help us answer this question? To analyze, let's consider some numbers here. The mass of this cricket ball is 150 grams. Let's say the speed at which it hits my hand before the catch is 10 meters per second. So the initial velocity is 10 meters per second. Now what is the final velocity after the catch? That's right, it's 0 meter per second. Now let's say I didn't take the catch in the correct way. So the ball comes to a sudden stop in say 0.03 seconds. So how do we calculate the force in this case? By Newton's second law of motion, force equals the rate of change of momentum. The formula is F equal to mass into acceleration, which is mass into final velocity minus initial velocity by time. Now plugging in the values, we get the force as minus 50 Newton. There's a negative sign because it's a retarding force. But we'll ignore the sign for now. So my hand feels a force of 50 Newton during the catch. Now let's catch the ball the correct way. As you can see, by moving my hand down, I'm increasing the time of the catch. Let's say the time here is 1 second. Other numbers remaining the same, what is the force now? Let's use the formula F equal to ma. Plugging in the values, we get the force of minus 1.5 Newton. So that's a retarding force of 1.5 Newton. It's 33 times lesser than the previous value. Now, why is that? Because in this case, the time of the catch is increased. Now, time is in the denominator in the formula. So the rate of change of momentum is lesser. As a result, my hand experiences a smaller force. So as you can see, Newton's second law of motion helps us explain this example. Now let's play some tennis. While playing tennis, you want to hit the ball fast and in a direction that makes it hard for the other player to get to the ball. So how do you do that? By hitting it like this. When we want to hit the ball hard and in a direction we want it to go, a greater force causes a greater change of momentum in the ball and makes it go faster. The ball moves in a direction that we hit it in. So which law of motion tells us this? That's right, it's Newton's second law of motion, which states that the rate of change of linear momentum is directly proportional to the applied force, and it takes place in the direction of the force. So if you hit the ball with a greater force, the ball will go faster. There will be a greater change of momentum in the ball, and the change of momentum takes place in the direction of the force. You might have seen this magic trick before where they pull the tablecloth and the things don't fall. Now I'm not a magician, so please wish me luck. Let's try. Ready? 1, 2, 3. Whoa! I'm happy it worked. Now let's take a look at the action replay and see which Newton's law is behind this magic trick. As you saw there, when I pulled the tablecloth really quickly, these things hardly moved or didn't fall. So how do you explain that? That's right, it's due to their inertia. Inertia is the laziness of a body. Now there are two types of inertia: inertia of rest and inertia of motion. So which one do you think is applicable in this case? That's right, it's the inertia of rest. The things on the table were at rest and they want to remain at rest. So when I pull the tablecloth really quickly, they resist that momentary force, and that's how they don't fall. So Newton's first law regarding inertia explains this example. Let's see what we can learn from this balloon here. I'm going to release this balloon and you'll see that it moves around on its own. So are you ready? Let's start. Now let's take a look at the action replay. So how do you explain the motion of the balloon? When I released it, the balloon pushes out the air inside it with a force. The air exerts a force on the balloon, making it move forward. Now, are these forces equal and opposite? Yes. So which law are we talking about? That's right, it's Newton's third law of motion. And this same law explains how a rocket works. A rocket exerts a forces on the gases backwards, and the gases exert an equal and opposite force on the rocket forwards, making the rocket move, just like this balloon. So here are the 6 simple everyday examples we looked at for Newton's laws of motion. Now that we are done with the 3 laws of motion, are you ready to take a look at the top 3 questions on this topic? Friends, I would like you to try solving these questions. And do post your answers and doubts in the comments below. I promise to reply to your comments as soon as possible. So I'll move away and you pause the video and give these questions a shot. I hope you enjoyed watching the video. I would encourage you to look around and see if you can find Newton's laws of motion in your everyday lives. Do let us know what examples you experienced by putting it in the comments below. Inspired by Sir Isaac Newton, I'm going to tell you to leave your inertia of rest. Take action and apply your force on the subscribe button. And my reaction is going to be, thanks for subscribing to my channel.